Good morning, everyone, and welcome to our presentation. Today, we'll be discussing the specifications and standards for vessels used in our procedures. On this first slide, you'll see a comparison table that outlines the dimensions for vessels according to USP IP and ELECTROLAB limits. We have details for the inside diameter, which ranges from 98 to 106 millimeters for USP IP, and is specified as 104 millimeters plus or minus 0.5 millimeters for ELECTROLAB. The height varies from 160 to 210 millimeters in the USP IP standards, with ELECTROLAB specifying it at approximately 170.5 millimeters, plus or minus 1 millimeter. For the hemisphere, the USP IP limits are between 49 and 53 millimeters, while ELECTROLAB sets it between 50 and 52 millimeters. It's important to note that residue can remain in the scratches formed on the vessel, which can cause carryover and hinder accurate observation. This overview sets the stage for understanding the precise specifications we need to adhere to in our testing processes. Let's take a closer look at the water bath, which is an essential part of the USP Chapter 711. This device is used to maintain samples or reagents at a precise, constant temperature, which is crucial for many laboratory procedures. When working with a water bath, accuracy and consistency are key because even small fluctuations can affect your results. It's important to ensure the water level is appropriate, covering the samples but not overflowing, to promote even heat distribution. Regular cleaning and maintenance are also vital to prevent contamination and ensure reliable performance over time. Connecting this to our overall theme, a well-maintained water bath helps us achieve the precision and reliability that USP standards demand, ensuring the integrity of our testing processes. So, understanding how to properly use and care for this equipment is fundamental to upholding quality in our lab work. When should you filter a sample? Well, it's best to do it either immediately after the sample is collected or during the actual sampling process. This helps ensure the sample remains representative and uncontaminated. Now, regarding the filter position, it should be placed as close to the vessel as possible, ideally from the sampling zone itself. That's where cannula filters come into play. They're positioned right at the point of sampling to capture the sample directly. When selecting filters, there are several key factors to consider. First is compatibility. Make sure the filter material or make is chemically compatible with the active pharmaceutical ingredient, or API, and any other excipients present. This is crucial to prevent any adverse reactions or contamination. Next is efficiency, which depends on choosing the right pore size. The pore size should be suited to the formulation. So, for smaller particles, a finer filter might be necessary, whereas for larger particles, a coarser filter will do. Leachability is also important. Consider the interference that might come from the filter's material of construction, or MOC. You want a filter that doesn't leach substances into your sample, which could skew your analysis. And finally, size matters, specifically the diameter of the filter. This should be based on the volume you need to withdraw. The right size ensures efficient filtration without unnecessary waste or delays. All these points are part of what we need to validate in our analytical method, ensuring that our sampling process is both reliable and reproducible. In summary, choosing the right filter involves balancing compatibility, efficiency, leachability, and size, each of which plays a crucial role in maintaining sample integrity and ensuring accurate analysis. Dissodose. When we're talking about the medium volume, it's essential that it stays within plus or minus 1% of the specified value. This level of accuracy is critical because it ensures consistency and reliability in our procedures. According to the USP Guideline on Procedures for Mechanical Calibration and Performance Verification, specifically for Test Apparatus 1 and Apparatus 2, maintaining this precision is a must. Now, focusing on media volume accuracy, we need to regularly verify that our measurements are within that tight tolerance. This helps us guarantee the quality of our testing and ensures compliance with industry standards. So, overall, keeping our medium volume accurate is a fundamental part of maintaining the integrity of our calibration processes and ensuring our results are trustworthy. Now, let's look at some key observations regarding USB Chapter 711. One of the main advantages is that it serves as an important tool during method development and formulation optimization. Essentially, it helps us understand how different variables influence the dissolution process. Dissolution patterns are particularly useful because they give us insights into the formulation variables at play. If we see a certain pattern, it can point us toward what might be affecting the drug release. Another critical benefit is that this chapter is helpful for those who are unable to observe real-time dissolution tests. It provides a way to interpret results indirectly, which can be invaluable in certain scenarios. And finally, it's a perfect tool when evaluating out-of-specification or out-of-trend data. If a dissolution result falls outside expected ranges or trends, this chapter helps us identify potential issues and understand the underlying causes. Overall, these points reinforce how USP 711 is a vital resource in ensuring quality and consistency in our dissolution testing processes. Let's now look at the factors to be considered while sampling, as outlined in USB Chapters 711, 1092, and 724. First, the sampling zone is crucial. It's important to choose the right location from where to withdraw the samples to ensure they are representative. Next, the sampling duration should be within acceptable limits, typically within plus or minus 2% of the designated time point. For example, if you're sampling at 30 minutes, a window of plus or minus 36 seconds is acceptable. Regarding sample volume, the limits are also around 2% of the aliquot volume you've decided on. So, for a 10 milliliter sample, an acceptable variation would be plus or minus 0.2 milliliters. It's also essential to ensure that the aliquot volume doesn't exceed 1% of the total volume of the dissolution medium to prevent altering the system's behavior. Replenishment of the medium is generally not preferred because it can disturb the dosage unit in the vessel, but it may be necessary when maintaining sink conditions becomes a challenge, especially if there are many sampling points. When it comes to the sampling probe position during the test run, selecting the proper position helps ensure consistency and accuracy. Lastly, follow the proper steps for manual sampling carefully to maintain the integrity of the process and obtain reliable results. Overall, paying attention to these factors helps ensure the sampling process is precise, reproducible, and in line with quality standards. Let's talk about the sampling zone for the paddle apparatus, specifically USP Type 2. When we consider where to take our samples, the key point is to focus on the area between the top of the stirring element and the surface of the dissolution medium. This zone is crucial because it ensures we're capturing a representative sample of the dissolution process. According to USP Chapter 711, for both the USP apparatus Type I, which is the basket, and the USP apparatus Type II, which is the paddle, the sampling zone should be located midway between the top of the stirring element and the medium surface. It's also important to keep this zone at least 1 centimeter away from the vessel wall. This prevents any potential wall effects that could skew our sampling results. So, to sum up, the key points are selecting a sampling zone that is midway between the stirring element and the medium surface, and ensuring it's not less than 1 centimeter from the vessel wall. This helps us maintain consistency and accuracy in our dissolution testing, which is vital for the overall reliability of our results. Let's talk about sampling duration. This is a crucial aspect because it directly impacts the quality and reliability of our data. Essentially, sampling duration refers to the length of time we collect data during an observation or measurement period. Choosing the right sampling duration is a balancing act. If it's too short, we might miss important variations or fail to capture the full picture. On the other hand, If it's too long, we could waste resources or introduce unnecessary complexity. It's important to consider the nature of what we're studying, whether the process or behavior is steady or variable over time. For stable processes, shorter sampling periods might suffice. But for more dynamic systems, longer durations ensure we get a representative sample. Connecting this to our overall goal, selecting an appropriate sampling duration helps us gather accurate, meaningful data that informs better decision-making. So, always think about the specific context and what you're trying to achieve when determining how long to sample. Let's take a closer look at Slide 9, which discusses the USB CHAP 1092 and the two main options for sampling probe position, immersed and non-immersed. Starting with the immersed option, here the cannula tip of the manifold rests right at the top surface of the medium. When it's time to sample, the cannula tip dives into the vessel. This method is typically used when we have filters attached directly to the cannula tip. On the other hand, the non-immersed option keeps the cannula tip in the air, so it remains above the medium surface. When sampling, it dives into the vessel, just like the immersed method. This setup is used when no filters are attached to the cannula tip. It's important to note that the immersed method, with filters attached, is not recommended by USB, whereas the non-immersed method is actually recommended. So, in summary, we have these two options, immersed and non-immersed, and each has specific use cases and recommendations based on USB guidelines. Understanding these differences is crucial for ensuring accurate and compliant sampling procedures. Let's talk about cannula position, which is a critical aspect of our procedure. Ensuring the correct placement of the cannula is essential for both safety and effectiveness. First, we want to make sure that the cannula is positioned in the optimal location within the target vessel. This means it should be well within the lumen, not touching the vessel wall, to minimize any risk of trauma or dislodgement. Next, it's important to consider the angle of insertion. A proper angle helps in maintaining stable access and reduces the chance of dislodgement during the procedure. Also, we need to confirm that the cannula is not kinked or bent, as that could impede flow and compromise the procedure's success. Another key point is to verify placement with appropriate imaging or clinical signs, depending on the context. This ensures we're in the right spot and that the cannula functions as intended. Throughout the procedure, continuous monitoring of the cannula position is vital. Any movement or signs of displacement should prompt immediate reassessment. Overall, precise cannula positioning is a cornerstone of a successful and safe intervention. It connects directly to the theme of meticulous technique and attention to detail, which are essential for optimal patient outcomes. Now, let's go through the steps for manual sampling. First, you want to insert the sampling cannula into the vessel immediately before reaching the sample time point. It's important to position the tip of the cannula right in the sampling zone to get an accurate representation of the sample. Once you've reached the designated time point, start taking the sample promptly. If needed, you can replenish the same volume of sample using the dissolution media to maintain the system's volume and conditions. After collecting the sample, carefully remove the cannula from the vessel. Remember, it's crucial not to leave the cannula inside the vessel for safety and to prevent contamination. These steps ensure that your sampling process is precise, consistent, and aligned with the overall goal of accurate dissolution testing. Now, let's talk about the documentation of data, specifically following the ALCOA principles. When should this be done? As soon as the data is generated. It's crucial to record data immediately to ensure accuracy and integrity. This is a key part of maintaining data integrity, which we've emphasized throughout this presentation. Proper documentation helps us prove that our data is reliable and trustworthy. Think of it as creating a clear, transparent record that supports the validity of our work. Remember, timely and accurate documentation isn't just a best practice. It's a core requirement for compliant and credible data management. So, always document promptly and thoroughly to uphold the highest standards of data integrity. Let's talk about backup and restore. It's crucial that data backup is available for everything important: methods, users, audit trails, test reports, and logbooks. And of course, these backup files must be encrypted to ensure security and protect sensitive information. Moving on to audit trail, it's essential to track user activities like logins, logouts, password changes, and any incorrect user attempts. For test-related activities, we need to log when tests start if they are aborted, when power failures occur, communication issues, and when tests are completed. Any modifications or deletions related to operations should also be captured to maintain a clear record of all activities. Now, regarding e-signatures, electronic records may be signed digitally, but these signatures must have the same legal weight as handwritten signatures within the organization. They should be permanently linked to the specific record they pertain to and include the exact time and date they were applied. This ensures authenticity and traceability. Let's also touch on user activation and deactivation, which are important for managing access. We need a multi-level access system to control permissions effectively. Additionally, implementing password expiry policies helps enforce regular password updates, enhancing overall security. Finally, I want to emphasize data integrity requirements. Maintaining data integrity means ensuring that all data remains accurate, consistent, and reliable throughout its life cycle. This is fundamental to our overall data security and compliance efforts, tying everything together in a robust system that supports trustworthy operations. Now, let's move on to slide 14, which focuses on data integrity solutions. As we all know, maintaining data integrity is crucial for ensuring that our information remains accurate, consistent, and trustworthy over time. This slide highlights the key solutions that Sentinai offers to address this vital aspect. These solutions are designed to detect, prevent, and correct any discrepancies or errors in data, helping us safeguard the quality and reliability of our information systems. By implementing robust data integrity measures, we can reduce risks, improve decision-making, and ensure compliance with regulatory standards. Remember, in the broader context of our presentation, these solutions are foundational to building a secure and resilient data environment. Let's take a closer look at KLOUDFACE. This is the third key concept we're exploring today. KLOUDFACE represents a new approach to digital identity management. It emphasizes security, privacy, and user control, which are essential in today's increasingly digital world. The idea is to give users more authority over their personal data while still enabling seamless interactions online. This ties into our overall theme of creating more trustworthy and efficient digital ecosystems. By implementing solutions like KLOUDFACE, we can enhance user confidence and foster innovation in how we handle digital identities. So, understanding this concept is crucial as we move toward more secure and user-centric digital environments. Let's take a closer look at Trusty 8 Gen 2. This part is really crucial because it highlights the ongoing evolution in digital trust and consumer protection. As you can see, Trusty has been a key player in establishing standards that help companies build and maintain consumer trust. The second generation, Trusty 8 Gen 2, introduces new frameworks and updated best practices that better address today's digital landscape. It emphasizes transparency, privacy, and data security, elements that are more important than ever. By implementing these enhanced standards, organizations can not only meet regulatory requirements, but also foster stronger relationships with their users. This aligns perfectly with our overall theme of building trust in digital environments. So, in essence, Trusty 8 Gen 2 represents a significant step forward in creating a safer, more trustworthy online ecosystem for everyone. Let's take a closer look at the detailed understanding of dissolution operations and their benefits. First, it's important to grasp the key processes involved in dissolution. This includes how materials are broken down efficiently, ensuring maximum extraction and purity. Understanding these mechanics helps us optimize the entire operation, making it more effective and cost-efficient. Next, I want to highlight the benefits of mastering these operations. When we have a thorough understanding, we can reduce processing times, improve product quality, and minimize waste. This knowledge also allows us to troubleshoot issues more quickly, leading to smoother operations overall. Connecting this to the broader theme of our presentation, it emphasizes that deep operational knowledge isn't just technical. It directly impacts our productivity, sustainability, and bottom line. So, investing time in understanding dissolution processes pays off in multiple ways, reinforcing our strategic goals for efficiency and excellence. Let's take a closer look at some of the key aspects of dissolution operations and the benefits they bring. First, the rinsing cycle is essential for ensuring that any residual substances are thoroughly washed away, which helps maintain the integrity of the process and reduces contamination risks. Next, cannula position plays a critical role. Proper placement ensures optimal flow and reduces complications during operations. Filtration is another crucial element, as it helps remove particulates and impurities, ensuring the purity of the solution. Manifold lead time is about the importance of planning ahead. Having the manifold ready in advance minimizes delays and keeps the process running smoothly. Then we have the dynamic dive, which refers to adjusting parameters in real time to optimize performance. Auto-dilution is a useful feature that automatically adjusts concentrations, saving time and reducing manual errors. Lastly, manual sampling remains important for verifying quality and consistency, providing a direct check that everything is proceeding as it should. All these points connect to the overall theme of improving efficiency, safety, and reliability in dissolution operations, ultimately leading to better outcomes and higher quality results. Now, let's move on to slide 19, which focuses on cross-validation with the manual method. This is a crucial step to ensure our automated processes are accurate and reliable. When we talk about validation points, the first one is contamination. It's essential to check that our samples aren't contaminated at any stage, as this could lead to false results. Next, we look at carryover, which refers to residual samples from previous runs that might affect the current one. Ensuring minimal carryover is vital for accuracy. Another key point is dilution, because sometimes samples need to be diluted, and we need to verify that this process is consistent and precise. We also need to validate the rinsing and cleaning cycles, making sure they're effective in removing residues so that there's no cross-contamination between samples. Lastly, we compare automatic sampling versus manual sampling. While automation offers efficiency, manual sampling can serve as a reliable reference point to validate the automated system's performance. All these points are interconnected and contribute to the overall reliability of our testing process. By thoroughly cross-validating with the manual method, we reinforce the integrity and accuracy of our results, aligning with our goal of maintaining high-quality standards throughout the system. Now, let's talk about contamination and carryover. These are important concepts to understand in our field because they can significantly impact the integrity of our results. Contamination refers to the unintended presence of foreign substances, which can come from our environment, equipment, or personnel. It's something we always want to minimize to ensure our data is accurate. Carryover, on the other hand, happens when residual material from a previous sample contaminates the next one. This is especially critical in sequential analyses or high-sensitivity testing. It can lead to false positives or skewed results, which can compromise the entire process. Both contamination and carryover highlight the importance of proper cleaning, handling, and protocol adherence. They remind us that vigilance is key to maintaining the quality and reliability of our work. Throughout this presentation, we've emphasized that understanding and controlling these factors is vital for achieving consistent, trustworthy outcomes. Now, let's take a closer look at some of the innovative rinsing cycle features that add real value to automation. First up is the split rinse DM. This feature allows us to divide the rinsing process into separate stages, which helps improve efficiency and ensures thorough cleaning. Then we have loop back TM, a clever mechanism that recirculates rinse water back into the system, reducing water consumption and optimizing resource use. Next is the intense rinse with air purge TM. This combines a powerful rinse with an air purge, effectively removing residual contaminants and drying the system more quickly. These advanced rinsing cycles are not just about cleaning, they're about enhancing overall process efficiency, reducing operational costs, and improving quality. When we integrate these features into automation, it becomes a game changer, providing consistent, high-quality results with less manual intervention. So, in the broader context of our presentation, these innovations highlight how smart design and automation go hand in hand to deliver better, faster, and more reliable cleaning processes. Let's take a closer look at the different rinsing cycles we use in our process. First, there's the rinse by loopback, which essentially involves circulating the rinse fluid back through the system to ensure thorough cleaning. This method helps remove residual contaminants effectively. Next, we have the rinse by intense rinse and air purge. This cycle ramps up the rinsing intensity and then uses an air purge to blow out any remaining particles or liquids. It's a crucial step for achieving a high level of cleanliness, especially before critical operations. Then, there's the rinse by intense rinse and loopback, combining the deep cleaning power of intense rinsing with the recirculation loop to maximize contamination removal. It's often used when we need to ensure the system is as clean as possible. Finally, we have the rinse by air purge alone, which relies solely on compressed air to dry and clear out the system. This step is particularly important for removing moisture and preparing the system for the next phase. Understanding these different rinsing cycles and their purposes helps us maintain the integrity and performance of our equipment. Each cycle plays a vital role in ensuring a clean, efficient process, and selecting the right one depends on the specific requirements at each stage. Let's take a closer look at loopback TM. This concept is really about creating a continuous feedback loop, which is essential for refining processes and improving outcomes. It allows us to gather insights, assess performance, and make adjustments in real time. By integrating loopback TM into our workflow, we ensure that we're always learning and evolving. This ties directly into our overall theme of continuous improvement and agility. The key here is that it's not just about collecting data, but actively using that information to drive smarter decisions. Ultimately, loopback TM helps us stay aligned with our goals and adapt quickly to changing conditions. Now, let's take a closer look at the intense rinse DM with air purge. This is a crucial step in our process that really enhances efficiency. Essentially, what we're doing here is combining a powerful rinse with an air purge to ensure thorough cleaning and drying. The air purge helps to remove any residual liquids or contaminants that might be left behind after rinsing. This not only speeds up the drying process, but also improves the overall cleanliness and quality of the final product. It's a key component that ties into our overall theme of optimizing performance while maintaining high standards of hygiene and precision. By integrating this step, we're ensuring that each cycle is as effective and reliable as possible. Now, let's talk about the final piece of the puzzle, intense with air purge. This technology is designed to enhance cleaning efficiency by combining a powerful rinse with an air purge. The key here is that the air purge helps to remove residual liquids and contaminants more effectively, ensuring a cleaner and more thorough process. It's especially useful in situations where residual fluid might cause issues later on. By integrating this step, we're not just improving cleaning quality, but also reducing downtime and preventing potential contamination. Overall, this innovation ties back to our goal of delivering safer, more reliable results through smarter cleaning solutions.